Well, hi guys, we're going to have a look at integration using the CAS handheld device today. Now, I need to let you know that at our school we use the Texas Instruments TI CAS handheld device, and some of the information I'll give you would be specific to that, but a lot of it won't be, and you'll be able to apply it to whatever handheld device you use. Okay, so let's get started. There's some very interesting and useful information in this session. Now, first of all, we have to use the CAS handheld device to evaluate that thing, which is the integral of the square root of 1 minus x squared with respect to x from 0 to a half. Well, that's very, very easy on the CAS handheld. Very easy indeed. So that's how you do it. And it'll spit out the answer very quick smart. Now, just to let you know that on the TI device you use Shift plus for integration. You'll get the integration template with the terminals and space to put your terminals in, space to put your function in, and space to put your x in your dx term. Okay. While we're at it, for derivatives you use the shortcut key Shift minus. Right, they're very handy. You don't have to go to the catalogue, don't have to go to the book. Just put the shortcut keys in, and they are great. Alright, so next one. We have to find the area of the region bounded by the graph y equals log x and x equals 2, and the x-axis by first of all using a CAS handheld device to evaluate that thing, and secondly using an inverse function, which I want to show you in great detail, because this bit here is something that you really do need to know how to do. Okay, so first of all, that's the easy bit. You just go Shift plus, put in that information there, and hit the Enter key, and what do you get? Bob's your uncle. Very easy, yes? Why don't you do that? Pause the video and do that, okay? And see whether you can do it, because it's important to know how to do it, not just watch what I'm showing you, okay? Now, this is part B. There's the graph there. There's the graph of log x. There's the line x equals 2, and there's the x-axis. So what we're actually interested in doing here is getting this little sort of triangular-ish area here integrated. Okay, the area under this. Now, as you know, guys, we haven't showed you. It's not in the course to show you how to analytically integrate log x just like that. It actually, there is an answer to it. It's actually x log x minus x, but you haven't been taught that. So we'll assume that that's just a mystery and we don't know how to do it. Okay? Because we don't, as far as the course is concerned. Now, yes, now let me just show you. I'm going to call this area 1 and this one area 2. And we're going to do this. We're going to work out A1 in a roundabout method by first of all working out the area of this rectangle here, which is easy to do. Then we're going to work out A2 directly, which is also very easy as it turns out. And then we're going to subtract A2 from the total rectangular area to get A1. That's our game plan. Okay, I call it the roundabout method. It's very, very exciting. Okay, so that's they're the coordinates of that point there, 0 and log 2. And we've got log 2 is this vertical height here, okay, of our rectangle, and this width here is 2 units long. That coordinate there is x is 2, okay. So therefore we want that one there. We don't know how to do it. It's not analytically possible for us. We can't evaluate with calculus. So therefore, but we can evaluate A2 using the inverse function y equals e to the x. This is very exciting, and I'm going to show you in a minute on the next screen. Yes, we can evaluate A1 plus A2 because that's that rectangle that I just showed you over there, and that's actually 2 times log 2 the base e. Okay, that's easy. Yes, the area of a rectangle. So therefore, by difference, A1, we're going to work it out as the area of the rectangle, the total area of the rectangle, A1 plus A2 minus A2, which I'll show you how to do in a minute. It's quite ingenious. Okay, over we go. Now, look at all this. I've got the original graph here. I've got log x here for you. Okay, and I've drawn in a little sort of a line here to sort of help you visualize this rectangular bit. Okay, that's the line y equals log 2. And over here, ladies and gentlemen, this work of art is the original graph here, plus its inverse, okay? And I've drawn a line x equals log 2 here, okay? X equals log 2 there. And this, okay, now the reason there's method in my madness, why did I draw the inverse? Well, I'm going to use that to work out the equivalent of this area here, which remember was A2, okay? Now, that's the graph of y equals log x, that's the inverse graph of y equals e to the x, okay? And on the inverse graph, everything is reversed in terms of x and y, okay? So you'll see that if you look here, I've got the line here. I've got the line here, y equals 2, to correspond with the one where I had x equals 2. Where I had y equals log 2 here, I've got x equals log 2 there. Okay, where this log graph crosses the x-axis here at x equals 1, then the inverse crosses the y-axis at y equals 1, because everything's reversed in terms of x and y. Yes, my oh my. Yes, flying high with all this information. So, and this is the inverse function, yes. Now, that's area A2, and look, this area here, therefore, is the equivalent. It is exactly the same as area A2, except that it's orientated this way, so that the rectangles would be vertical rectangles here, as in the way that we're normally used to integrating. It's a more normal looking thing. I'll show you. So A2 areas are identical. Okay, the A2 areas are identical in y equals log x. These ones here are identical to this, well, that area. That area there is identical to that area there, isn't it? Yes? Okay, so, yes, right? That's what I said. Now, the graphs, but A2 is easy. Now, this is the difference. This is why I went to all the trouble of drawing this inverse. A2 is easy to evaluate from the inverse function, okay, but it's not so easy to evaluate here. In fact, it's a mess. If you try and evaluate it like that with our normal vertical rectangles, you'll run into all kinds of trouble. You have a go at it and see. You'll know what I mean. It doesn't work, and we end up with trying to evaluate something with log x again in it, okay? So that's not going to work, but this one is going to work beautifully, because basically we do this. Two vertical rectangles, and yes, the area is actually it's just e to the x, the integral of e to the x with respect to x from x going from 0 to log 2. Now that's easy to do, okay, and that you get e to the log 2 with the base e minus 1, and as you know, e to the log 2 is just 2. Okay, so it's 2 minus 1, which gets you 1. So this area here with the green vertical rectangles is just 1, right? But we weren't able to work it out analytically over here. So this inverse trick is rather beautiful, okay? So that's what they mean up here by saying using the inverse function, okay? And I want you to remember this technique very, very well, the roundabout technique, okay? When you can't integrate something analytically, it's a very, very enormously strong probability that they're asking you to remember and to know how to do this roundabout technique using inverse, inverse functions. Okay. So A2 equals 1, and therefore A1 is the total rectangular area which we worked out on the previous screen minus A2, which comes to what? 2 log 2 minus 1, right? The other one was, the total rectangular area was 2 log 2 minus this one here, which is 1, and that's what you get. That's what you get, guys. Isn't it great? Yes, so can you please sock that away in your memory banks? This is the roundabout technique for when you can't evaluate something analytically, okay? They do it for trig functions, and they also do it for log functions, okay? They're the two kinds of functions which lend themselves to this technique in a rather beautiful way. Now, over the screen, I'm going to show you the Wolfman way of doing this without having to actually go to all the trouble of drawing the inverse and figuring that out. Okay, it's really good, and it uses rectangles on their sides for this area over here. So let's go up and away. Here's the alternative. Now there's our original graph. I don't have to draw the inverse for this graph. I think this is rather beautiful, so just watch this. So we need A1. That's A1, and we know that A1 was that. We discovered that earlier. Yes. Yes, we can't do it using calculus. We know that. But we can work out A1 and A2. That's the combined area, which is the area of the rectangle, which is 2 log 2, as we discovered in the previous screens. And that height is log 2, and that height is log 2, that width there is 2, so that's the area of the rectangle, yes. Now for A2, now watch this, this is where we change from the previous technique. For A2, guys, this one in here, we're going to use integration of A2, the A2 area directly using sideways rectangles. Watch this. Right? Good heavens, you say. Yes, well, look, it's really logical and it's really beautiful. This is why I always want you to think of integration as areas of rectangles, because you can untangle any mess if you just go back to the rectangles, okay? So A2 is now, look, the sideways height of these rectangles, if you like, the sideways height is the x value, right? Relative to the y-axis, it's just the x value, right? And the widths are little delta y's. Isn't that cute? Yes, there's the heights, the x's, and there's the widths, the delta y's. Okay, everything's reversed, but it works mighty fine, as you'll see. Just watch this, because we're integrating from y is 0, which is here, to y is log 2, which is up there. Okay, so that's the y span over which we are integrating. Now, all we've got to do, guys, is get this x as a function of y, and everything's beautiful. Okay, we will be flying high, yes? Yes, now we know that y equals log x, therefore e to the y equals x. There it is, x is in terms of y, and it's kind of like an inversey thing again, like we had on the previous screen. Yes, except that it's x equals e to the y. We don't have to go to all the trouble of drawing the inverse graph of y equals e to the x, because this is really easier with the rectangles on their sides, but it's a very similar process, yes? So therefore A2 is e to the y with respect to y from 0 to log 2, my oh my, flying high, and there it is, okay? It's the same thing as we got on the previous screen. So it's just going to be 2 minus 1, which is 1, yes? Easier, isn't it? Much easier. So therefore A1 is the total rectangular area minus A2, which is the same as we got before, which is 2 log 2 minus 1. Yes, and we're done. Yes, and we're done. And we had fun, didn't we? Yes. Okay, what have we got now? Well, this thing, we have to do, we've got the graph of y equals e to the, is that e to the sine x minus 2, as shown, and we have to, we've got to get using a CAS handheld device, we have to find the area, the shaded regions. Well, guys, this one here, look, why don't you pause the video and have a go, and I won't say any more. You come back when you're ready. Okay? Well, how did you go? Did you realise that you can't just do the integral of this from pi on 2 to 3 pi on 2? That'd be the trap to fall into, because this integral here will be cancelling out part of this integral here, and you won't get a net area. You'll get a net integral, okay, where you had some cancelling of positives with negative integrals, which is a disaster when you're looking for the area of the shaded regions. So what we need to do is work out this point of this intercept here, then integrate from there to there, and then from there to there, strip away pluses and minuses, and then just add up the numbers. That's the way to go, guys. Yeah. So you need to analyse your rectangles again to work out whether the integrals are going to be positive or negative. I can tell you right now, if we integrate from here, from pi on 2 forwards to 3 pi on 2, this integral will be positive, this integral will be negative, okay? Yes, so you have to take care of that and make sure you don't mess it up when you're trying to work out what your areas are. Okay, point of intersection, well, that's the point of intersection of the graph with the x-axis, right? And there she be. Oh my goodness, what's all that? So solve e to the sine x minus 2 equals naught with respect to x. Yes, this with statement is vitally important, because if you just do that solve thing without all this conditional thing in here about the where the x can go from and to, you will end up with general solution palaver and gobbledygook, which will send us all into a mind-bending state of algebraic mayhem. Yes, you do. So you have to be very specific. If you're doing solves with trig functions, you have to state the domain over which you want the thing solved. Okay, and it's been very obliging and giving us this value here. You see, you try that. If you try that without that, you see what you get. Get all these parameters and goodness knows what else, and it just sends you into a state of numbness, numbness and limbo, which you don't want to be in. So, all right, let's just work with that now. And now here's our rectangles. I always do this analysis. This rectangle here for this area, this rectangle here for this area. So that's a positive. I'm going to go from pi on 2 to 3 pi on 2. Therefore, that's a positive width and that's a positive height, which is going to get me a positive integral. So that's good. However, this one's a positive width and it's a negative height. I've drawn it in red just to send the alarm bells ringing. That's negative. So that's going to be a negative integral. So we will have to take that into account. Positive integral, negative integral. Right. So what I did, guys, was I worked out this first one as it was, because that'll get me a positive integral result with from pi on 2 to this x-intercept which we found up here, and then I've gone negative this integral here, because the integral in and of itself is already negative, right? So if you go minus a minus, you get a plus, and then everything's good again, and you get this from your CAS. Yeah, that's the area, combined area under that graph between pi on 2 and 3 pi on 2. And Bob's your uncle again. Okay, well, let's keep going. What do we got here? Consider the function defined as capital F of x, going from cos t dt from 0 to, note that, from 0 to x. Now this is the first of a few of these which I'm going to show you in successive screens here, where these are actually, if you plotted these on your graphics section of your CAS handheld, every one of these, if you put that in on your graph screen as an integral, it has to evaluate it as an integral. Every single point of x, see, because the x is on the terminal here, and it has to evaluate this cos function with this cos function from 0 up to x to get a value of x, which is very, very processor hungry. Okay, and it can take a few seconds before the points start to emerge on the screen. Even though the thing is a powerful computer in its own right, it still has a big headache computing all this, where every single x point is actually evaluated as an integral. The other thing is, when you're doing these on the calculator, guys, you must not use x in here when you've got x on the terminal. The calculator will freak out. You have to use what you call a dummy variable. A dummy variable, no offence to Mr. T here, you're not a dummy, you're just a dummy variable in this case, Mr. T. So you'll see that this just evaluates as a function of x anyway when we work it out. See, look, it goes like this. F of x, capital F of x equals, now what's the integral of cos? Well, it's sine, isn't it? So it's just going to be sine t evaluated from 0 to x, which just gets you sine x minus sine 0, or just sine x. So yes, it is a function of x. It is a function of x. But there's a very, very great difference between you entering this in your graph screen, which is easy for the CAS handheld to evaluate, and this into your graph screen, which means that every single x point has to be evaluated as an integral, which is very much more processor hungry. Okay? And remember that dummy variable, will you please? You have to use that, otherwise your calculator will give you an error. So now this time we've got an example of this. We're actually plotting the graph of, well, really it's the area under the graph of y equals x squared, if you like, or in this case t squared, okay, but evaluated from 0 to any value x as an integral. So it's actually working out areas, right, or integrals for every single value of x. It's working out the integral from 0 up to that value of x. to get a point to plot on the graph screen. So it's very processor hungry. Excuse me. So yes, x is the terminal of the integral. This means that f of x is the area under the graph of y equals t squared between 0 and x, and every value of f of x is an area between 0 and x, so it's very, very processor hungry. So there we go, f of x equals that, which comes to, yes, that's the thing, that's the thing. I've added this, that's what it actually is, but we weren't asked for that, but I just wanted to show you. This is what I've put into my graph calculator screen, okay, and it's given me a done, everything's good. You notice I used the dummy variable though. If I didn't use t or p or q or r or anything else that I like, r squared dr or p squared dp or whatever, if I used x in there, the calculator would freak out. I wouldn't get any further and I would just get error messages and general upset from the calculator. Now, yes, as I've said, every value of x computes in the CAS as an integral, so it's very processor hungry. If you sketch the graph of f of x that is, if you sketch it on CAS, every point needs to be computed as an integral before being plotted. Now, I've also given you this warning in here. Here it comes. Do not use x in the integrand when x is written as a terminal. You will get an error if you do. Okay, let's over the screen. There it is. That's what you get. But I can't show you in real time the process that the calculator goes through in plotting this. Usually it takes, on my calculator, it might take, it seems like it's not doing anything. Then about 2 or 3 seconds later you'll start to get a few points starting to emerge. Then fairly quickly after that it'll just start banging them all in, and you'll get this curve, but it's noticeable. It's happening in real time, whereas normally on a CAS handheld it's just bingo, there it is, you know. But this time you can see that it's struggling under the weight of the task that you give it. Yes, that's right. I'm just saying there it takes longer than normal because it's working out every point as an integral, and it's very processor hungry, okay? Alright. Now, what's this one? Plot the graph of, same thing guys, except that it's 1 over t this time. Before it was 1 over t squared, wasn't it? Yes. So this is, again, we're evaluating between 1 and x as an integral to get every single value of f of x is evaluated as an integral of this function between 1 and x, okay? So it's the same sort of thing. I've basically repeated all the same palaver that I had on the previous screen. You can read that at your leisure. And that's actually, that should read, wait a minute, I suppose I better fix that just a moment. Yes, I've just fixed those, I changed those little f of x's into capital F of x's, that's all, because basically that was the terminology they used in the problem statement up here. So I'm just trying to be a little bit correct with my notation, but it doesn't make any difference to what I was saying. Just trying not to confuse you. So you get that. That's what you get, actually. That's what you get. So you're going to get a log graph, okay? Which is what we expect as the anti-diff of this thing anyway. Now, yes, it's just log x. See, it is an f of x, right? Even though you use this dummy variable in here, this dummy variable doesn't really make any difference to the outcome. It's just going to be a function of x, right? That's what I'm trying to say. But don't go using x in this part of the integrand, because the CAS handheld gets extremely confused and thinks, well, what's going on here? We've got x in here, we've got x in there, we've got x all over the place. It needs to evaluate the x bit at the end, okay? Without any confusion. That's what it's all about. Yes, don't write x in there, as I was saying. And same thing, it's evaluating every point as an integral, so it's very processor hungry. Yes, yes, every point needs to be computed as an integral before being plotted. The poor old calculator, we're giving it lots of grief. But you know, the calculators are so powerful these days. I often tell my students that the simple little CAS handheld devices you use these days are more powerful than the computers they used to put the man on the moon in 1969. So that's a pretty staggering thought, isn't it? And that's true, I believe. Anyway, so there's your graph. That's what you get. Okay, that's a graph where every single point has been computed as an integral. So that is a very, very enormous task for your CAS Handheld. Now, what else? Yes, it's slow because it's processor hungry. Final question for you. This is a little bit of a flavour of some more questions will be coming up in a future video, which will be basically entitled Solving Differential Equations Using a Definite Integral. But this is just a little an appetizer, just to get you used to the idea, okay? I thought I'd throw it in. It's my own creation. Show that sine x equals sine a plus, look at that. It looks confusing, doesn't it? Show that sine x equals sine a plus the integral of a to x of cos p dp. Now, this is just a dummy variable, guys. This will become very clear in a moment when I just re-express this a little bit in a way that you will get, right? Based on what we've just been doing earlier, right, we can say that cos of p, integral of cos of p with respect to p from a to x, right, this is just a dummy variable, right? That'll be sine of p evaluated between a and x, yes, which would be sine of x minus sine of a, okay? So therefore, you can see that it's just fallen into our laps. That really says what that question is asking us to show by simply just getting this term here and adding it to both sides. You can see that sine x equals sine a plus that thing there. Well, I really should put, I'll change that to a p. Just a minute, abracadabra, and I've fixed it. Okay, so I've made that cos p dp, which is what I need to do. You can't go putting x in there after I've been raving and ranting and lecturing you about it. I can't go doing it, can I? So that's the answer, and that's what we had to show, okay? Right, so now that's it, and that's the end, and you're a star, and you'll go far. Huzzah and hurrah, and we'll see you in a future video, and all the best to you. Have a great day, and bye.